Well, we've seen that we can get some interesting looking plots by plotting out these vector functions. But I want to point something out that's very important to section 11.1 and 11.2. And that is, we've cobbled together different scalar functions to make vector functions. But when it comes to taking a, for instance, derivative or a limit or an integral of one of these vector functions, we can deal with each component, the x, the y, and z, independently. Okay? So if we ask the question, what is the limit of the vector r, t, as t goes to some value, whether it's infinity or t naught? Okay? Well, that's simply, I mean, this thing is x, y, and z, and so all we have to do is figure out, and we know how to do this, the limit of the function of t I as t goes to t naught plus, and then once again, I mean, you know, I'm not going to write them all out here, but the limit of the gt as t goes to t naught times j. So in other words, we just deal with the x and y independently. We ask the question, okay, well, that worked. What about if we ask the question, what about the derivative of this vector function? What's that going to be like? Is that some exotic thing that we have to, you know, really huge formula? No. What we do basically is the derivative of f dt times I plus derivative of g dt times j plus the derivative of h dt times k. In other words, each one of these is dealt with independently. It really makes some sense because the vector function is a composite, and when we want to integrate or differentiate or take a limit, we simply look at the parts separately to get our answer.